Welcome to Almost Here, Round the Corner Future Technology podcast with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more.
Hi, this is Richard Jacobs with Future Tech Podcast. Almost here, around the corner technology. And today I'm speaking with Brandon Sweeney, co-founder and CTO of TriFusion.co, a 3D printing company focused on sports market and also, bio use of 3D products. But better introduction would come from Brandon. How you doing, sir?
I'm doing well. How are you?
Okay, good. Yeah, thanks for being here. If you would, I'm sure you can describe what TriFusion does a lot better than I could. So if you would just give a quick background.
Sure. So TriFusion, it's really about using 3D printing for medical devices. Specifically, we're targeting prosthetic and orthotic devices. These are devices that a person who suffers from limb loss, either an amputation or a congenital birth defect, who doesn't have a limb, would use a prosthetic device to walk around every day. This is also something our veterans would use. So somebody who's lost a limb in the service of our country, they need a prosthetic device to be able to walk around and carry out kind of a daily normal life. So we're all about using 3D printing and the ability to manufacture a custom bespoke and one-off device that's really necessary in order to make these products. We're implementing 3D printing technology to do that.
Yeah, what got you into this particular part of 3D printing and 3D printing in general? Were you guys in the military, or what's the reason?
So yeah, I'll go into my background a little bit. That's kind of where this started. I started working for the Army Research Labs when I was in high school. So I grew up in the Maryland area, Baltimore, northern Baltimore, and I started working for the Aberdeen Proving Grounds at the Army Research Labs, and I was working a lot with robotic devices, and we would use 3D printing to prototype designs. But we had this big issue that the parts that we would print out, they would fracture in between the layers. They would just kind of peel apart. And it was great. You know, you could design something in CAD and then click print, and a couple hours later, your part was just sitting there and waiting for you. So that aspect we loved. It's so fast compared to traditional machine shop turnaround times, and the complexity that you can put into those designs is unbelievable. But there was always this hesitation there because we couldn't use it for a final full-strength part because of this fracture issue in between the layers. So I had always had this kind of experience with 3D printing, and you know, in the back of my mind, I kind of carried that around with me. Like, you know, how can we solve this issue? There's got to be a way to address this interlayer weakness that's inherent to 3D printed parts. And then, so I went to college, kept on working for the Army Research Labs, and as I was finishing up college at Rensselaer Polytechnic, I really knew that I wanted to go into and get my PhD, do some research. I had been working a lot with nanomaterials, and I started my PhD at Texas Tech University with my advisor, Dr. Micah Green, and we worked with carbon nanotubes a lot, and he had a project where they were using carbon nanotubes and microwaves to detect very low concentrations of carbon nanotubes in biological samples. And the reason is because carbon nanotubes, they interact with electromagnetic energy pretty uniquely in comparison to other materials. They heat up super fast. You put a little bit of carbon nanotube powder in a microwave oven, and the stuff basically explodes. So when I kind of had some interaction with that technique, I thought, this is a really interesting material that we could use to couple with 3D printing materials in order to address this weakness. So along with my advisor, we invented this method where we take these nanomaterials, the carbon nanotubes, and we put them into the 3D printer feedstock, which is filament. It looks kind of like weed whacker line. And the way that we put those materials into the filament allows them to be deposited right at the interfaces of that 3D printed part. And then when you apply an electromagnetic field, that material, it heats up rapidly and it welds the layers together. So just like you would weld like an I-beam together in a skyscraper, you take a point source of heat like a torch and you weld the interface together. And we do the exact same thing for 3D printing, except we do it at the nanoscale because of the materials that we're using.
So this is like a super glue for the layers that make up a lot of 3D printed objects.
Yeah, it's like out of the hundreds or thousands of layers of little tiny bits of plastic that you're squirting out to make your part, we are going in and welding every one of those together by using these kind of unique materials and then the application of electromagnetic energy.
That's really smart. So what kind of materials can this be used for? Which ones is it compatible with and which ones not?
So right now we're really focused on thermoplastic materials. When you're talking about plastics, there's generally two different kinds of plastics. There's thermoplastics and thermoset plastic materials. And thermosets are like epoxies and rubbers. Our technology potentially can work for those, but right now we're really focused on thermoplastics. And thermoplastics, when you heat them up, they soften and then they start to flow. So the vast majority of plastic parts that you interact with on a day-to-day basis are made using thermoplastics. So we're using the heating response of those nanomaterials to locally heat up the interface of those thermoplastics to get them to soften and then bond together. So that's one of the unique properties of thermoplastics is that when you heat them up, you can reshape them, reform them, weld them together, as opposed to thermosets. Once they're solidified, the part is done. It's set in its shape. You can't heat it up to reform it.
Okay, gotcha. So what have you seen experimentally this has done to the 3D printed objects you're making, before and after using the carbon nanotube to weld them? How much stronger are they? What other properties are affected?
Yeah, so with a traditional 3D printed part that doesn't have our technology, when you print something, and when you print a part, you're laying down these kind of slices of material. Like you'll print out one layer, and then the bed or the print head moves up a little bit, and then you print out another layer of material, and you keep on doing that over and over again to build your part up in the Z direction. So that's generally how 3D printing works. And when you test the properties of these parts, the mechanical properties, say you were to print out a little material, like a bar, to test its strength, when you print it vertically on the bed so that all of those interfaces are aligned perpendicular to the pulling direction, you only get about half of the strength of the base material. If you were to injection mold or machine a similar test bar, you would see that that's kind of like the baseline full strength of the part. But if you 3D print out the same shape vertically, it's at best half the strength, and that's a big issue because when you're making a part and you design it, if it's only half of the strength of the normal material, then everything else has to get bumped up by at least a factor of 2. So you either have to have twice the wall thickness or twice the size and shape of it to make it strong enough. And for a lot of designs, that just doesn't work. So when we do our welding process, we're able to recover between 95 to 98% of the strength of the part. So that's a huge increase of the strength, and it makes our parts basically the equivalent of an injection molded or a machined counterpart. And in the world of 3D printing, that's night and day. That's the difference between your part fracturing on you and you didn't even know that it was broken, or the device lasting for many years without any issue at all.
Yeah, that's great. That addresses a big time weakness of 3D printed objects. I would think that if an object experiences shear force along the plane of a layer, that's where it would be weakest, or maybe not.
Yeah, so polymers, they generally do fail in shear when they're pulled. And our technology, it's really addressing both of those material weaknesses. So when you weld the layer and the interfaces together, you're getting increased polymer interdiffusion across that interface. So if you imagine like two spaghetti noodles that are separated, really in order to get the strongest bond, we want the noodles to be as mixed together as possible across an interface. If the polymer chains, if they're not entangled, then it's pretty weak. And with our technology and that thermal energy being directed just at the interface, we're able to energetically excite the polymer chains and cause them to diffuse into each other, and that provides both tensile and shear strength.
Yeah, makes sense. Yeah, this is a great thing you figured out. So you don't have to use too much material. You could probably use finer dimensions. The part's stronger, it lasts longer. Just all good things because of this. Right?
That's right. Yeah.
Do the electrical properties of a part change because of the fused carbon nanotubes in each layer, or is that not affected at all?
So, that is one of the other interesting aspects to our materials. They are technically electrically conducting. It's not the same as a metal, so it's not enough to really pass a lot of current through it, but it does work very well for anti-static or ESD applications. So we've actually had some interest from the military who's interested in using this for EMI shielding and electrostatic discharge for aerospace components or other materials that need those properties. And the really nice thing is that we only use a very tiny amount of active material, the carbon nanotubes, in this process, so that means we can do it a lot cheaper than a counterpart material that's filled with a lot of conductive particles.
Okay, makes sense. So getting back to the applications that you're using it for, so you're 3D printing prosthetics, what kind are you tending to print most often, arms or legs, or just parts of them, and what applications are they using?
We're really focused on lower limbs right now, so legs. We're targeting both transfemoral and transtibial sockets. So the main reason is those are the limbs that are going to be most debilitating to not have. So if you don't have an arm, that's not good, but you can still walk around, you can go shopping, you can drive a car. Those things are pretty easy for you. But if you're missing a lower limb, that's debilitating. You either have a prosthetic device or you're living your life in a wheelchair, one of the two. And to have a prosthetic device with today's methods, a lower limb can cost somewhere between $10,000 and $50,000 for all the components. And generally those devices, they wear out every 3 to 5 years and need to be replaced. And healthcare costs are, insurance is just not really covering the majority of that. The user and patient is left to bear the cost of the vast majority for that 3D print that limb. And with 3D printing technology, we're able to provide a device that meets the needs of the patient at a factor of 5 or 10 less than current technologies. So all in, we can produce devices somewhere between $500 and $5,000, depending on the complexity and the materials that are involved to a patient. And we can also do it a lot faster. So normally, one of these devices, it involves a lot of manual labor, and it takes somewhere between 4 and 6 weeks minimum to get the custom device made for a patient. And with 3D printing technology, all of that gets expedited. So we can do this in as little as 48 hours.
Wow, all right. So how much better are your leg prostheses than normal? You said they wear out every 3 to 5 years. Are they more comfortable because they're customized? You do a scan of the person's, I don't know what you call the part that the prosthetic would adhere to, or where it joins the body. But do you scan that area? Like, what's the process, and what are the improvements?
Yeah, so the methodology that we use right now, there is a big software component to this because all of our design work is done digitally. We've teamed up with a company called Standard Cyborg. They're out in San Francisco, and they're really the software sister company to our hardware company. And we've partnered up with them so that they have a partner clinic and a prosthetist or an orthotist who uses their app on a iPad, and the iPad has a 3D scanner hooked up to it, and you'll go in and you'll scan in a person's limb geometry. So if they have a transfemoral or a transtibial amputation, you will use the 3D scanner to get the digital image of their residual limb. That gives you a CAD file, which the prosthetist can go into the software program. They can manipulate that. A lot of times they will do volume reductions, or they'll kind of sand in and smooth areas out, or they'll flare some areas in or out. And that's all based on the fact that your limb, it's very much a fluid object. It's not this rigid, hard thing. If you push on your knee and your leg, you see that there's areas that are softer than others. You've got ligaments, you've got bone. It's a very complex object. So simply scanning it in to get the shape, that isn't sufficient to have like the perfect fit device because everything changes when you put your weight on it. And when you're walking around, you're going to have the areas of bone, they're not going to move at all. So that needs to be fit very well. But your muscles and your tendons, those are all going to be moving dynamically. So to make the prosthetic device fit comfortably, a prosthetist who's trained to do this process, they need to know how to adjust the limb in order to make it fit well and be comfortable and not cause rashes or rubbing that's going to irritate your skin. So that's a really highly technical skill. They're trained to do that. So we're partnering up with prosthetists to do that process. And then once they have a design that they're comfortable with, we're looking at a socket here. You could think of it kind of like, I don't know, a ski boot or some other really tightly fitting shoe that's going to be rigid, essentially. These devices, they're not made out of the soft leathers that your shoes are typically made out of. These are typically carbon fiber devices. And that has to accept the residual limb and then support their weight as the patient's walking around throughout their daily activities. And so the fit has to be right to make it comfortable. And once that prosthetist, they have the shape that they want, we will take that file and then we print it out using our materials and technology. And we send that back to the clinic, and the clinic, they'll take the components that we sent to them and do the final assembly and the final fitment of those devices. And actually, one of the major benefits of our process And this kind of goes back to what I was talking about before, the difference between thermoplastics and thermosets, is that thermoplastics, again, they can be reheated and shaped to change them a little bit. So say we send a patient a device and they've walked around on it for a day or two, and they figure out, hey, there's a pressure point right where my adductor muscle is. Can you take this socket and adjust it a little bit so it's more comfortable? Right now, with current technologies, you can't do that. Once they've made a carbon fiber socket with an epoxy resin and it's cured and set, that's the shape of it. You can't do anything to adjust the fit. So if they need something changed and you've already made the final definitive socket, then you have to throw it away, scrap it, and start over again. And that's a huge waste of time and money to do that process over again. With our technology, you can take the socket that's been printed out, and you can take a heat gun, and right where it needs to be adjusted, you can heat it up a little bit to the point where the plastic softens, and then they can adjust the fit as necessary. And then when it cools back down, the shape gets set again. So we think that alone really offers a major benefit to patients so that throughout the life of using their device, they can come back as necessary and have it tweaked here and there for comfort. Whereas before, if it didn't fit right, sorry, you got to live with that for 3 years before you get a new one. And that must be a pain.
That's amazing. Wow. That's really cool what you guys are doing.
Thank you.
So how many patients have you made limbs for? And what's been their feedback and commentary if you're at that stage?
So yeah, we have 2 different product lines out right now. The first major product line is for something called check sockets. A check socket is a clear version of the socket for a patient, and that is like the first step that a clinician will use to check the fitment of the design. So typically they'll make a check socket out of like a polyethylene terephthalate sheet that's drawn over a plaster version of the patient's limb, and then they'll fit that onto them and check to see if they got everything right or if it needs to be adjusted. So our first major product line is a 3D printed version of that. We can do it a lot faster and a lot more accurately using the digital scanning and 3D printing process. And to date, I actually don't have a full count, but we're sending out between 3 and 6 check sockets every week. We're teaming up with that company, Standard Cyborg, to supply these devices, and we're starting out this technology kind of on the smaller scale, and this upcoming year we're going to be growing that to much larger volumes as the need grows with our partner clinics. So we have probably around 50 or so check sockets that are out in the field right now that have been tested and used for this fitment process. And then the other major product line, which is really where our technology hits, is the final definitive sockets. And this is actually in beta phase right now. So we're not selling these devices yet because we have to go through a clinical trial phase in order to validate that these devices are safe. And in compliance with the FDA and good manufacturing processes, we need to make sure that we've fully refined the technology and that people who are using our devices every day will be safe in doing so. So right now we've gotten through 3 phases of testing. We've worked with 3 different patients to test out our advanced materials and welding process, and the results have been really, really good. There's still some things that we need to refine as we continue working towards the clinical study and validating all the materials and the lifetime use of the devices. But we're on track to be getting this technology out into the market by mid to late next year.
That's fantastic. get this going? Are you going to go to a full prosthetic leg, or what else do you see is needed more immediately?
So I think that in everything that we do with our technology, the greatest benefit comes when you're dealing with devices that are custom. So to that end, we're working with the prosthetic limbs. The next phase that we'll be kind of entering into is orthotic devices. So this is like knee braces, ankle braces, neck braces, back braces for scoliosis. So there's a lot of applications in patient orthotic devices that could benefit from this customized and accurate scanning, modeling, and then printing technology that we've been developing. So that's our next market that we're going to be entering into. That's an easy win for us because it shares a lot of the same process control parameters and steps in making these devices, and we'll be able to enter into that market fairly rapidly. And then down the road, there's two other main areas that we want to get into with this technology. The first is working with sporting protective equipment. So we've seen a lot of need for custom helmets, protective helmets, pads, and guards. Right now, you have small, medium, large. It's kind of a one-size-fits-all economy for these products. And as we know, people are all different sizes and shapes, and it's kind of critical for things like football helmets or knee pads and all these things that they fit properly for athletes to have the most comfort, so that they'll actually want to wear their protective equipment, and also so that the device can function at its best to absorb impact. Yeah.
Years ago, quick story, my dad used to ride motorcycles, and he had to get a custom helmet made because his head was, big. And if I try to wear a baseball hat, I have to put it on the last notch. My son is the same way, so yeah, I would love something like this. So good.
Yeah. I mean, this is a first-hand experience for almost everyone that you get something that's supposed to be, a wrist strap that, you go through the little notches of your wrist strap, and none of them really quite fits for you. It gets close, but it never really fits custom to you. So anytime there's an application where we can take digital scans of anyone's geometry and then use our modeling process and then printing process to create an exact custom fit device for you, then I think that's a big win for our technology, because that's exactly how 3D printing should be used. We'll probably never get into markets where it's designed for mass production. We don't claim to be able to make parts as quickly as an injection molder can. You can spit out thousands of parts per hour with big injection molding machines. So if it's a mass-produced device that doesn't need any customization, that's not really our market. But anything that involves humans and needs to be custom fit, we can really do a lot of good there. One other area would be for the military and law enforcement to create soft body armor. I don't know that we're going to be doing ballistic body armor anytime soon, but there are a lot of applications where having more custom fit devices that are designed for an individual user, the military, our soldiers could benefit from that. Our law enforcement and first responders could all benefit from that technology. So that's one of the other future markets that we're looking to get into.
Yeah, if a vest or some other device is comfortable, it's more likely to be worn, so it could easily save someone's life. It may ride up in the wrong spot or, not fit properly and not cover someone, so it makes total sense.
Yeah, that's right. Yep.
Interesting. So what, I understand your guys' focus on customized items. In general, though, what do you think is possible in the next few years, specifically in regards to what you guys do? And what do you think is still fantasy or it's going to be quite a while before you're able to do it. What's your dream goals for your technology?
So, specifically, I can share one example that we're working on right now. And this kind of goes back to creating a better fit for people. With current prosthetic technologies, you're using, aerospace grade materials. That's great. Carbon fiber, Kevlar materials to create a strong prosthetic socket. The only problem is that, it's a rigid device. It doesn't move or flex with the body as you move around. So, imagine walking around all day long in a pair of wooden or carbon fiber shoes. They'd be tough as nails, but your feet would start to hurt pretty bad after a couple of days of using those. What we want to do in the next couple of months here is continue developing a new method that we've worked on for blending together stiff and flexible materials so that you can create these gradients between your structural reinforcement and a more compliant and flexible area of the device. So, this is a major biomimetic approach here to go about making prosthetic devices. Our limbs are these really complex blend of hard and rigid materials, structural materials, your bone, to high tensile materials, your connective tissues, and then your muscle, the soft fatty tissue, and your skin. It's this blend of all these different materials. They all have different stiffnesses. And what we want to do is to create better fitting devices by matching certain materials to areas of the limb that need to be either reinforced or allowed to flex and move as you move. So you can imagine having windows, little areas where your muscles are that are going to blend into more of a flexible material. And then around the brim, the upper edge of the device, having that to be, gradient wise, moved from the hard, rigid, reinforcing material into, again, this flexible material will allow for much greater comfort so that you don't get pressure sores or other, major skin irritations where the hard device meets your soft tissue. So that's one of the concrete examples of how we're going to be using 3D printing materials and technologies to increase the fit and comfort of these devices, because right now that's just not really possible. You can't create gradients where a material flows from carbon fiber to an elastic part. You'd weaken the material, and it would involve thousands of man-hour labors crafting such a complex device. But when you get software into the mix and you can tell a computer, hey, I want this area to be flexible, and in this area I need it to be strong and reinforced. At the end of the day, all we do is click print and feed the materials into the printer, and it comes out with this beautiful amount of complexity in the design. And all we did was sat there and watched it print out. So I think that's one of the main areas that we are looking to advance here in the near term. And then in the future, I think it all comes down to starting to work with different kinds of materials. So I'd love the ability to print out metals and ceramics along with polymer components. I think it's still a little bit of a pipe dream. That might be 5 or 10 years out to the point where we could do that. But if we could print out an entire prosthetic device that didn't need any other components or attachment points, that would be amazing to have everything in one shot. And I think it's definitely on the horizon. It's just a question of when.
Very good. Okay. So for companies, individuals that you potentially could work with, what's the best way for them to contact your company?
You can go to our website right now, TriFusion.co, I guess there's been a lot of media that's kind of surrounded this after we won the Rice Business Plan competition. So if you just Google TriFusion, you can find us pretty easily. And I think in the future that really we'll be partnering with a lot of clinics. We're starting with clinics here in Texas. We're located in College Station, Texas. So we've been working with the Baylor College of Medicine in Houston and Center for the Intrepid in San Antonio. And then we have several partner clinics throughout in California. And I think that as we start to grow this technology, that really everything is just going to travel by word of mouth. The orthotics and prosthetics community is pretty well connected. So if they see people walking around with our devices, I think that they'll see the benefit of the technology, and we'll have some more customers there.
Okay, very good. Well, I appreciate you taking the time. This is a great service to a lot of people, this technology that you've come up with. And it's really cool that you're starting with the military. And, I think it's going to be a huge help to people that are disabled in general. So.
Yeah, thanks for taking the time to ask us some questions. We really appreciate your interest in our technology, and definitely we look to improve people's lives all across the board by using 3D printing, and we really hope to, it's been really cool. Some of the patients that we've worked with, as soon as they put the device on, you see their face light up, and they realize how quick the process was, how easy it was, and that's what fires us up. We get so motivated when we see that response from people and how much it can do to change their lives, and we want to be able to reach as many people as possible.
Very good. Okay, well, thanks for taking the time. I appreciate you being on the show.
Absolutely.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.